Hi everyone, my name is Yugandhara, and today I'll be talking about my project, which I've been working on the past few months, on phase transitions, and it's a computational investigation of them using the Ising model. And this project was mentored by Alex Strange and Mark Naring. All right, so first of all, what is a phase transition? A phase transition occurs essentially when a physical system changes from one state to another because of some external condition, like temperature. And a simple example of this is water. So as water increases its temperature, it reaches a critical temperature point where there's essentially no distinction between it being in its liquid state versus in its vapor state. So we can see on the graph over here, the temperature is increasing, and we see this little critical point which for me at least is the most interesting, where we can't really distinguish whether water is liquid or whether it's vapor. So for the systems which I've been studying, we can think about this transition in terms of order. And below a certain critical temperature, which is the point where a phase transition happens, these systems are usually more ordered. But above this critical temperature point, we have a disordered system. So the main question really is, at what critical temperature do these transitions occur at? So before I get into my work, I want to quickly go over a couple of broader applications of phase transitions. So the first is on gravitational waves. So earlier in the universe, massive phase transitions may have caused huge energy bubbles to form, expand, and crash into each other. And these collisions created powerful ripples in space called gravitational waves. And we can still detect these today to learn about the origin of our universe. The next one would be emergent spacetime. So instead of space just being a pre-existing background, this theory is suggesting that space itself is built from microscopic quantum building blocks. So just like how steam cools into liquid water, these like small quantum pieces would have undergone a phase transition that would condense in a way into a smoother continuous space that we live today. So you can sort of see over here we have these little blocks, and over time through such phase transition, it's evolving into this smoother space-time, which we're more familiar with. Okay, the last one would be black hole thermodynamics. So black holes have temperatures and they store heat, meaning that they can still also change states just the way water can turn into ice. And by studying these phase transitions or these state changes, theory predicts that black holes can shift between forms using the same phase transition rules as is used in everyday materials like water or anything else. Okay. So before I dive into my work, I wanted to quickly recap some concepts of entropy, temperature, and order. So imagine that we have a collection of spins that, and we're asking like how many different ways we can arrange them while having a particular number of spins pointing up. So the number of possible arrangements that a spin or a system can have is called multiplicity, and entropy is related to this. So entropy over here is symbolized by this equation, and this omega sign is the number of possible configurations, or the multiplicity, as I mentioned. And these systems, it's important to note that energy typically is favoring order, while entropy is favoring disorder. So in a system, depending on the temperature, when it's at a lower temperature, the system will want to minimize the amount of energy and have a very ordered system. But as the temperature is increasing, as you can see over here, this adds energy, and as a result, this increases disorder of the system. So temperature is this really important factor which determines whether entropy or energy is winning in the system's environment. Okay. So I've been using the Ising model in my project to sort of learn how to determine the critical temperatures of, certain systems which are either 1D or 2D or 3D. So in the Ising model, we've had the 1D and 2D Ising models being solved. The 3D one hasn't been solved yet. And we can see in a system like this, there are n number of particles on a d-dimensional lattice, and each carries a spin up or a spin down. So this one is an example of a 1D system, this is an example of a 2D system, and this over here is an example of a 3D system. And we can see each of these circles are different particles, and they would either be spin up or spin down. And each of these lines are showing that all these different particles are connected to each other, and they're called nearest neighbors. Over here, I have this equation for energy, which is essentially just showing us, the energy of the system, whether it's 1D, 2D, or 3D, and just a few factors which can affect the energy of these systems are the coupling constants and the magnetic fields. So the coupling constant is essentially just determining how many spins are up or down, and the magnetic field is just, a usual magnetic field which impacts the system. So over here, I'm also describing the order parameter, which I've used to determine how, or determine how the system goes from order to disorder. So I've denoted an order system as being m is equal to 1, and a disorder system as m is equal to 0. And this Ising model essentially allows us to capture universal features of phase transitions through these parameters. Okay. So in terms of methods, so I'm investigating how particle systems shift from order to disorder in 1D, 2D, and 3D systems. But the main challenge is that the number of possible spin configurations, they grow exponentially of a power of 2 to the power n. So even for a relatively small number of spins, let's say it's 10, you're calculating 2 to the power of 10 number of possible configurations. So essentially, direct calculations of these things are not practical or reasonable. So I've been using the Metropolis Monte Carlo method, which is ideally the best option. So going a bit more into this method, it's a fairly simple algorithm. So in terms of steps, we first start with choosing an initial state of the system. So it can be all up or all down, or it's randomized. And then the algorithm will essentially start choosing different sites. So it'll choose one site. It'll calculate whether, the change of energy, calculate the change of energy if the spin is flipped. If this change in energy is greater than 0, then it's going to generate a random number between 0 and 1, and only flip the spin if this randomized value is below a certain probability. And this probability is impacted based on the temperature and the change in energy as well. If, however, the change in energy is less than 0, then the system or the algorithm will just accept the flip and then go on to the next site. And this process is repeated over and over again until the algorithm is able to go through the entire system. Okay. So I'm going to start off with my results for a 1D system. So for a 1D Ising model, there is no phase transition because at any temperature above absolute 0, spins start flipping at random. So entropy is always going to win over energy. And as a result, the system is never ordered above absolute 0. And we can see over here, this is one of the results which I had for my 1D Ising model. And we can see that I'm using different sized systems. So for n is equal to 50, we have just like 50 particles in a row with each other. For n is equal to 200, we have 200 particles in a row. But we're seeing that the order parameter, which again represents, if it's at 1, then the system is very ordered. If the order parameter is equal to 0, then the system is approaching disorder. We can see that this is essentially just dropping off very quickly and going towards 0. And I do want to note that while I am saying that 1D systems don't have a phase transition, this graph over here is just a computational model. It's not perfect, and we don't have a very smooth depiction of how this system is changing as the temperature increases. So even if it does look like it does technically have a phase transition at a certain critical temperature value, it's not entirely accurate. So moving on to my results for the 2D and 3D system. So we can see over here in both the graphs that at the absolute value of 0 for the temperature, the order is at m is equal to 1 for both the 2D and the 3D systems. However, as the temperature is increasing, the system is eventually going to reach its critical temperature point, which is shown when the graph is just quickly at a slope and then approaching 0. And as the temperature increases, the system is approaching the critical point and eventually reaches almost m is equal to 0 or a disordered state. And as you can notice, the critical temperature for a 3D Ising model is higher than that of a 2D Ising model, and this is because of the number of nearest neighbors for each system. So in a 2D Ising model, there are four nearest neighbors, while for a 3D Ising model, there are six. So as a result, with the 3D Ising model having more neighbors, the interaction between them is much stronger. So it takes higher temperature and hence higher energy for the system to go from an ordered to a disordered state. Okay. So just as a quick overview of my results, for a 1D Ising model system, it has nearest neighbors of 2 because, as I showed in the diagram a few slides ago, it was just a couple of particles which are right next to each other, and this has no phase transition. For a 2D system with 4 nearest neighbors, there's a theoretical critical temperature point of 2.27. My simulation had a critical temperature of around 2.25. So if I, for example, increase the number of points, which I'm, using to create these plots, I would probably get a smoother graph, which would show a more accurate depiction of this critical temperature. And similarly for the 3D system, there are 6 nearest neighbors. The 3D system doesn't have a theoretical value of the critical temperature, but computationally it's been approximated to around 4.5. And my simulation has a critical temperature of around 4.4. So again, if I increase the number of points I'm using, I will be able to get a more accurate result. Yeah, thank you so much.